Okay. So welcome everyone to our tech talk. Before introducing our speaker, and we are really happy to have Paul, who jumped in at the last minute, I'll give some housekeeping information. So make sure that you sign in and please RSVP so we can better prepare for the next session. Please text 274 for CME attendance, 2 CME attendance for CME credit. Use the chat feature in BlueJeans if you have any technical questions. Make sure you subscribe to the series to learn about the upcoming tech talks. And the next one is also by Paul, and that will be using hurdle models to analyze zero inflated count data on November 3rd, so next month. And you can see the full schedule on the ACCEL website, and all the previous presentations are available on our website, DE-CTR.org. So we are really excited to have Paul Kolm giving this talk today. I think it's going to be really, really interesting about meta-analysis. Paul is a Director of Biostatistics at Christiana Care and also a very active member of our ACCEL CTR. And thank you very much for being here.
So this presentation is controversial, and there's a lot of sort of, I guess, doubt about the validity and the usefulness of meta-analysis. It's been around for a long time, but there's also been I think a kind of proliferation of meta-analyses in the literature. I review for the Journal of the American College of Cardiology, and I've probably seen a dozen meta-analyses papers submitted since the summer. Now, for one thing, they're really easy to review because everybody knows how to do a meta-analysis. So the statistics, are pretty straightforward. There's all kinds of software to do them. But the question is how valid are they? So what I would like to do is to sort of go through meta-analysis as far as the methods are concerned and what a meta-analysis is from the methodological side. And then I want to talk about and illustrate the issue of what I call combinability of studies. And then finally, I want to talk about the probably the most controversial part of meta-analysis, and that is that there are those who think that meta-analyses are essentially uninterpretable. And so I'm going to kind of present their view and then talk about a little bit of my view. Okay, so as I meta-analyses has been around actually for quite some time, and there's a website, and I think most everybody that, at least as far as the articles that I've reviewed, cite the Cochrane website as far as sort of the way to do and present meta-analyses. So if you're interested in that, you can go online, look at their website. So the most really important part of meta-analysis is the data abstraction. So typically you do this with a literature by doing a literature search, and most of the time this is done in two stages. The first stage, or the initial review, is usually for content. In other words, you're wanting to put together or combine studies that obviously are looking at the same outcome. So you need to go through all the articles that may have come up in your literature search and sort out any that don't actually address the question that you're asking. Then a second review is usually then going through the ones that you've selected from the first one and then finding out if they actually have the data, if they've presented the data that you can use in the meta-analysis, because oftentimes there are articles that deal with the content that you're interested in, but they don't present the data that you would need to actually do a meta-analysis. So obviously that you can use those studies. And then you need at least 2 people to do that, probably more, but you've got to have some notion of consensus in selecting the articles. And from my perspective, the major issue in doing meta-analysis is the issue of combinability of studies. Even though you have studies that purport to measure the same outcome and have the same treatments, can they be combined in the meta-analysis? I'll give an illustration of that. Okay, so some concepts on the statistics of meta-analysis. I've presented this before, I think, in other contexts, so I think everybody probably is at least familiar with these, is the concept of a fixed effect or a random effect. And in statistical analyses, a fixed effect is the effects attributed to a finite set of levels of a factor. And primarily what we're interested in here is like a treatment effect. So they get, in the illustration I'm going to use, they get PCI or optimal medical therapy. So that's a fixed effect. There's no other levels of those. So we call that a fixed effect. On the other hand, in many studies we have random effects. In other words, it's more or less a random selection from the possible universe of levels of a factor. So, for example, in many, if you have randomized clinical trials and they've enrolled patients from different sites or different healthcare systems, we regard that as a random effect because obviously you can't include every site, every hospital, for example, in your analysis, or in your study. So what you have is more or less a random sample, although in reality it's not random because if you are doing a randomized trial, you're selecting sites that you know are going to enroll the patients you want. So, but at least that's the idea, that it's only a sample of the potential universe. So, for example, sites or hospitals, geographic regions might be another. Many trials are international, that they enroll patients from different countries. So those would be example of random effects. Patients that are enrolled are always a random effect. In any analysis you do, patients are a random effect. So another major concept we need to talk about in regard to meta-analysis is heterogeneity. And so what we're talking about here are obviously when you combine studies together, those studies are not always going to agree as far as the outcome. In other words, they may get different results. And so the question is, are those differences between the studies due to random sampling variability or chance? Or is there some other thing that's at play, some other reason why there's differences between the study as far as their results are concerned? So the size of the differences that the studies find, as well as the direction. In other words, one study might find in favor of one treatment, but another study doing the same thing finds in favor of the other treatment. So, when you combine those together, obviously that's going to cause heterogeneity between the studies. Okay, so, yeah.
So I've seen in meta-analyses to account for heterogeneity between studies, they often use,
Yes.
Or if they have subgroups, they'll use random effects. Sometimes they'll show random effects and fixed effects, but usually I see random effects in the context of very heterogeneous studies.
Yes, that's the traditional way of doing that. And most studies report both the fixed effects and the random effects results, but they usually will do random effects to account for the heterogeneity between sites.
And so I've had trouble interpreting those. You know, a random effects model might show one result, and a fixed effects model might show something different, and I don't know which one to trust.
Okay.
So I guess they're put side by side.
So that's where we're going.
Okay.
So if you have to leave before the final slide,
okay. I'll pick it up on the ITV.
So here is probably, this would be the most important slide in the presentation. So what you need to understand is that when we do meta-analysis, what we're doing is that we're taking the results from each individual study and we're statistically combining, or computationally combining those results into a summary statistic. And so that's either going to be a mean difference if we have a continuous outcome that we're looking at, or an odds ratio or risk ratio if we're looking at a dichotomous outcome. We define the precision of each individual estimate is weighted by 1 over the variance of the study, in the study.
So each estimate here you are talking about each study, its relative risk or each odds ratio that is published by a study.
That has each odds ratio or mean difference has variability associated with it within each individual study. And so variance, of course, that's dependent on sample size. So generally the bigger your sample size, the less the variance. The smaller the study, the bigger the variance. And so when we come up with this summary statistic across all studies, what that actually is a weighted average, where the weights are the precision. In other words, it's 1 over the variance, dependent on sample size of the individual study. So this is the computation for the overall effect, whether it's an odds ratio or difference or whatever it is the sum of the weights times the odds ratio or whatever divided by the sum of the weights. Now, the only thing you don't have to really remember all this, except that remember when I get to the end here and talking about how you interpret the results, that's what the summary statistic is based on. The key here is this weighted, is the weight here, the one over the variance. It's related sample size of the individual study. Okay, so there's a statistic that you'll see in meta-analyses called Cochran's Q. And you can see that for those of you familiar with analysis of variance, this is kind of like a sum of squares. So this is, in a sense, a measure of the heterogeneity among the studies. Okay. So it's the sum of the weights, and then the sum of the weights times the difference between each individual odds ratio and the summary ratio difference. Okay, it turns out that this is distributed as a chi-square with degrees of freedom equal to k-1, where k is the number of studies you have. So that means obviously that you can get a p-value for the Q statistic. However, and I know I've kind of said this in other contexts before, but basically when you see the p-value for this, kind of ignore it. And so it's subject to, obviously, depending on the number of studies, so it can be underpowered or it can be overpowered. So it's kind of not not particularly meaningful to talk about whether Q statistic is statistically significant or not. What is considered more important to present in the meta-analysis, what's called the I-squared statistic. And the I-squared statistic is just making a percentage out of the Q statistic minus this degrees of freedom divided by the statistic itself. And so obviously this is going to range from 0 to 100%. And this is sort of an index then of how much heterogeneity you have between the studies that you're trying to combine. And so if this is 0, then that means that the studies are homogeneous. In other words, any difference between the outcome, the odds ratio or the risk ratio, is just due to sampling error. And so if you have this case where you have 0% for the I-squared, then the random effect analysis and the fixed effects analysis will be the same. There won't be any difference. However, if you have a large I-squared, then what that means is that the results are not the same from study to study. And so then the question is how large is large, for I-squared? And so you'll see some sort of categorization of the I-squared statistic, like less than 25% is low, 20 to 50% is moderate, and above 50%. Another common one is to split this up, the last one here, into 50 to 75%, 75% of above. Okay, that's totally arbitrary. Somebody's idea of what to consider. But that's but whosever idea that was, it's always cited in the study. And so the question is how does heterogeneity affect the conclusions you make in analysis? Keep that question. Okay, and then finally here, what you'll often see in statistical or in meta-analyses presentations is what's called a funnel plot. And so basically what the funnel plot is a plot of the log of the odds ratios from each study against the standard error of that odds ratio, the log of the odds ratio. This is a measure of the variability within the study itself. And so what you want to see here is what's called a symmetric pattern. So obviously the studies up here, the lower the standard error, the smaller the standard error, the larger the study, because that's what standard error is based on. So what you want are all the large studies up here within the bounds, and then down here will be the smaller studies. So if you see something like this, where quite a number of the larger studies are outside of the confidence limits here, and that's that you have an asymmetric pattern, and that's telling you that there's some sort of bias going on here, that the larger studies are not consistently giving the same answer. Okay. So that's kind of some of the basic concepts of meta-analysis. Yeah. Okay.
Yeah. Is the thought that the studies are, that all the studies that you review are a random sample of some universe of all possible studies?
Yeah.
That year. Okay.
Right. So that's why it's typically people present the random effects analysis, because you're assuming that you have that your studies reflect a universe of studies and mostly what is saying is that there's some studies that look at the same thing but they weren't published. Okay. So there's a term that you'll see called publication bias. So what that means is that that there's a tendency to publish large studies that have significant results, but to not publish smaller studies that have non-significant results.
Does random effects account for publication bias?
It actually does not.
Okay.
which is what you would think it would do, and which I thought that was the case, but it turns out it's not really the case. Okay, so I want to do the next section here in with a specific example of why it's important. If you, for the time being, if you can just sort of accept the validity of doing a meta-analysis, why you can or can't combine some studies. And so a few years ago, there was a controversy. I don't know if it still exists, but there was a controversy regarding PCI, percutaneous coronary intervention, and medical therapy, as far as its effect on long-term survival in CAD patients, coronary artery disease patients, stable coronary artery disease patients. And actually, Dr. Weintraub was one of the people at the center of this controversy. So, in the late 1990s, I think it was, they started the COURAGE trial. So the COURAGE trial looked at PCI versus medical therapy. Basic finding was that there was no difference as far as long-term mortality, long-term survival that you could attribute to PCI. Well, this caused a big stir in the cardiovascular world, but there was a lot of controversy about that. So a little bit, or let me, I guess, go over the COURAGE trial first. So it had 3 different healthcare systems and then different hospitals within those healthcare systems. So between 1999 and 2004, they enrolled a little over 2,000. So this is a schematic of the trial to illustrate the difference in random and fixed effects. So they had 3 different healthcare systems, and then within each healthcare system, you would have a hospital, a number of different hospitals. I just have 2 for each here because that's all I could fit on them. And then within each site, you would enroll a number of patients, and they would be randomized to PCI or to medical therapy. So in this study, we actually, in effect, have 3 random effects. We have patients within hospitals, within healthcare systems. And then there is 1 fixed effect, which, of course, would be the treatment of PCI versus medical therapy. Okay, so the issues, and we've kind of already talked about this a little bit, that the reason that you include some factors as random effects in your study is because if they come from a cluster like a hospital or a healthcare system, that data is essentially correlated. In other words, they're not fairly independent. So you want to account for this. As we mentioned before, the published studies are considered a random effect because they're considered a sample of possible studies from the universe of studies. So after the controversy of the COURAGE trial and the publication of the results, there was this meta-analysis that was done shortly after that, where they took 16 randomized trials and 1 abstract. So they had 17 different studies that looked at PCI and medical therapy and compared those with respect to all-cause mortality. However, it turns out that the studies that they selected mixed patient types. And so, and of course, in looking at the study, I wouldn't know that, but the Courage investigators pointed this out, that some of the studies were looking at chronic CAD patients, but others were looking at post-MI patients. Now, don't ask me exactly what the difference is here. You'll have to ask Dr. Weintraub about that, or maybe some of explain that. But anyway, it's a different patient population.
And for patients who have ACS or MI, I mean, the treatment is really stunted. It's for acute MI, right? Whereas for stable angina, that's what the Courage was. So they are really different populations.
Yeah.
Is the risk of mortality different in those groups?
Yeah.
So, and then on top of that, there was a major MI trial, the occluded artery trial, that for whatever reasons was not included in this meta-analysis. So what I did then is I took the data, since get that, and I reanalyzed it, distinguishing the different patient types. In other words, I did basically a meta-regression where I have another factor in there, patient type besides treatment. So I'm looking at the treatment patient type interaction. And then I did a separate analysis where I included the OAK trial with the other post-MI studies that they had looked at. So here's their results. How visible this is, but you can see there's several things here. This is what's called a forest plot. So it plots, in this case, the odds ratios for each study. And then down here, it has the overall odds ratios and 95% confidence interval from the fixed effects and the random effects analysis. And so the way that this is plotted is that these squares or rectangles here, shaded ones, indicate the size of the study. So if you have a large box here, obviously that's a bigger study. The Courage is sort of the 900-pound gorilla among all these studies. And then some studies here have very small numbers. One study here, you can see that there's nothing for it, and that's because they had no events. No one died in these studies. The sample sizes were virtually the same, so obviously that has no impact on calculating the overall summary. So what you see here is that for the point estimates are the same here. The difference comes in the confidence intervals between the fixed and random effects analysis. And then they have the I-squared statistic down here, which is 17%. So, they call that kind of minor. So what I did is, as I already mentioned, I took the data, I separated out the studies with the different patient types, and did an analysis with those, looking at the interaction between treatment and did the same thing that they did. So it turns out that there was a significant patient type by treatment interaction, and so the odds ratios then between the two groups, you can see what is going on here, that there's no difference for the chronic CAD patients. There's no benefit of PCI, but there is for the post-MI.
Sort of a technical question. I think that But so when you do a meta-analysis, when you're actually doing it, you just have a big stack of papers. And you just take the data from the get the data from the original investigation.
Okay, well, usually you get it from the papers. Now, there are, and lately, because of the proliferation of studies and the availability of electronic data, some people have pooled the trials together. Now, in doing this, I think somehow think that pooling the data together makes it homogeneous, but of course it doesn't. So, in either case, it's actually really a meta-analysis because you're pooling study from different studies. So, obviously the conclusions that you would make are quite different, and then this is the forest plot with the two groups of patients sorted out. And there's kind of some interesting things here. First of all, notice that the I-squared of the CAD patients is 0. So what that means is that these are homogeneous. In other words, whatever differences you see here are just due to random sampling. That's not the case for the post-MI patients. In fact, the I-squared goes up a little bit to 21%. But you can see the differences here. There's no benefit of PCI for the CAD patients, but there is for the So there was another study, a major study done, the occluded artery trial. And as I say, for whatever reason, this was not included. Basically, what the O trial was looking at was the same treatment, PCI versus medical therapy, but it was looking at it in a different patient population than the COURAGE trial. And so they're going into a lot of detail here, but basically what it found was that the use of PCI there was no benefit of PCI for those. So then what I did was to take the O trial and include it with all these others and rerun meta-analysis for this set. And now you can see that they have kind of a really sort of interesting result here, that it really changes, because now notice first of all that the I-squared goes up to 47% when you include that. And then if you recompute the summary statistic, obviously there's not quite the significant benefit that there appeared to be when the O trial was not included. So the basic conclusion here is that there was no evidence of PCI benefit for chronic CAD patients, but there was for ACS patients or MI patients if you excluded the O trial. If you included the O trial, then that benefit was sort of disappeared. So the point of this is that when you read meta-analyses, you need to look carefully at who's included, what studies and what patients are included in the meta-analysis. Now, I'm not sure of the reason for the exclusions or the combining of the different, but some of the more cynical cardiologists call that cherry picking. Okay, so in other words, you basically pick the studies that will give you the result you want to hear. So that's, I guess, looking at the darker side of it, rather than just an oversight. So the point of this, of doing this, though, is focusing on the issue of combinability. In other words, just because studies have the same treatment and they're looking at the same outcome doesn't mean that you can just put them together and get results that are valid. Okay? So what we can basically conclude then in these here is that basically that the treatment effective PCI that we saw in that meta-analysis was due really to inappropriate pooling of studies or inclusion of studies. Okay, you can, if you're not watching or aware of that, you need to be that investigators are choosing their studies to include. Okay. So now, anyway, basically.
Have you ever seen is there a way of introducing like a term that captures quality of each study within the meta-analysis?
Okay, that's exactly where we're going.
Okay.
Okay.
Good.
Because if you remember from the formulas and the inverse of the variance, so basically what funnel plots are indicating is that there's some discordance between small studies and big studies. It doesn't say anything about the bias within individual studies, even though it's termed publication. It's purported to indicate publication bias. It doesn't have anything to do with actual bias within study. So, and the reason is obvious that whether the study is large or small, there can be biases in that study. So, for example, you might have protocol violations, or you have bad data in a big study just as well as in a small study. Or you can include patients that you shouldn't have or should have, So there's all kinds of reasons why a study might be biased. And the fact that it's large or small doesn't really make any difference. In fact, there's some of the literature, the references I have, has included studies that sort of show that even big, large studies are biased. So what happens, though, is when you do the computations to get the summary statistic, if you do a fixed effects analysis, what happens is that the larger studies will tend to reduce that inverse variance. Okay, so you have 1 over a big number versus 1 over a small number. So it turns out that in this case, if you just for a fixed effects analysis, that the pooled effect size will end up being the effect size of your largest or larger studies. The smaller ones are irrelevant. When you do a random effects analysis, though, what that does is it penalizes the larger studies so that you tend to, in a sense, bias the larger studies to make the smaller studies less biased. So what this means, and what is argued by some of the authors who take this particular view, is that when you do a meta-analysis, no matter whether you do a fixed effects analysis or a random effects analysis, it's computationally precise, but it's meaningless. Okay? So I've always been sort of skeptical of meta-analyses, but I think that this makes a good case for the fact that you really need to basically not trust, meta-analyses. So the meta-analysis is really it's only time it's actually meaningful if the I-squared is actually 0. So that means basically you have just random sampling variability in your studies, so you can make some conclusions about it. And so if it's greater than 0, however, then the only way that you can actually do a meaningful meta-analysis is to introduce what's called a quality adjuster. Exactly what you were talking about is that you need to introduce this term in the equation for Cochran's Q, and that way you get some estimate of the real bias within each study, whether it's large or small. But of course, that has issues as well. So whatever criteria you use to decide what is biased, what's not biased, and then how much bias there is if you're doing it on some sort of scale, is the reliability and validity of that. So obviously you're going to need some sort of consensus to come up with that. And then, of course, no matter what quality adjuster you come up with, somebody else is going to try and tear that down because it doesn't support what they would like to see in the results. So you're always going to get that controversy. But this particular idea here, I think, is really necessary to do a meaningful meta-analysis, is to some way get at that. And the argument here, of course, is, well, you can say, well, this is arbitrary. But that may be true. But at least when you do a meta-analysis, it has some meaning compared to just doing a meta-analysis without doing this, having really uninterpretable, results.
So is there a standard for the quality adjuster? You just decide, I put, all the clinical trials and who have at least, that have at least.
Well, in that case, then you've got to go through each study. You've got to have some sort of scale or.
But so that's something that each investigator decides themselves. There is not a standard that
there
for
is
quality adjuster.
Yes, although there is some literature, and for people who have done that, so that would be what I'm going to suggest. That would be the starting place to look at what other people have done. But basically, yes, you would have to go through, come up with some scale of bias, quality of the study, apply that to each study that you include in your meta-analysis. Right? So, the conclusions. So, if you want to do a meta-analysis, and you can see these guys. I'm just kidding. So, obviously, the picking the studies, selecting the studies is the most important step. As we've seen, you need to look at combinability. So if you want to do a meta-analysis, then maybe consider developing this study quality metric, incorporating that. I think that would be a much more powerful study than just doing a regular meta-analysis. And finally, if you're reading meta-analyses, read them extreme skepticism. So, and I want to end up here just by this is available, I believe, right, to everybody. So, in the references here, I've categorized these. The first three are the folks who are into the the quality metric study, and you can see by the title here where they're where they're at, that doing just an analysis without adjustment is. And then there are some other more famous or well-known folks that are associated with meta-analysis. If you find a paper, a meta-analysis paper, they'll probably have all these references and more. And then all kinds of. The last set here are the studies that looked at the Courage study and the OAT trial. So anyway, I hope that this will sort of give you kind of maybe a little bit different perspective than you may have had on meta-analyses in the past. All the statistical analyses that you can do, that this is the most essential for. Thank you. So I'm a little bit early, so questions or free to go eat lunch.
That's very depressing. Because more and more, I mean, you see in those literature, when we want to come up with ideas of research and things like that, there is always, you need to find a gap. You do a gap analysis, and you need to look at all the meta-analysis and see whether there was one, and if there is one, it's considered like the gold standard of, right. Okay, the question has been answered.
Yeah.
So what do we do now?
It does kind of question when you move from a systematic review to a meta-analysis. Maybe in a systematic review, you can be a little bit more nuanced and discuss strengths and weaknesses and think, but still kind of give an idea. Whereas a meta-analysis, because we have numbers attached, it just seems like people are like, oh, that's got to be the real thing, and that's the estimate. There's still all this nuance.
And one of the references I have here, if I remember which one, I can't remember. Might be this one. Actually has a little diagram starting at the bottom with basic science research, and then moving on up the steps, so to speak, and at the very top is meta-analysis, and the one right underneath that is systematic review. So obviously, that's supposedly one of the advantages of doing a meta-analysis, that you can attach numeric quantities to a systematic review, but obviously that's going to help.
Right.
So I think that to at least in part answer your question is that when you look at the meta-analyses and whatever it is to look at not only what they did, but what studies they combined, and you just have to use that for a basis for doing a lot of work yourself. New study, new question, or new meta-analysis. One of the things too that I notice about published meta-analyses, that oftentimes the I-squared will be 90% or better. It's like so. And it's sort of I think it's probably ignored. It's either ignored or the investigators don't understand what that means. So
it's just the random effects will take care of it.
Yeah. So that's why the last point there is read meta-analyses with a very high degree of skepticism.